Well, good morning, everybody, and welcome to Ellensburg, Washington, USA. This is Nick Zentner speaking. There's a chance this is working. You're looking at a title slide for today's talk. The local time is 11:49 a.m. Pacific time. Are we 5x5? Papagino says it's 5x5. Okay, there was a improv already. Okay, wonderful. We are working. Okay, terrific. Let me get you on a different camera. Let you enjoy the title slide of today's talk. And if you're watching this in replay, the program will begin in about 11 minutes. And I will put a chapter marker at the top of that. But let's hello, Adele in Auckland, New Zealand. Let me get to the wide camera and visit with a few of you, assuming that everything's still okay. Oh, Bryce, the rock. Bryce. I did not factor that part in, Bryce. This is good. Mind your P's and Q's now, Bryce. I challenged Bryce. In fact, I dared Bryce to sit in the very front row, and he's reluctantly doing it. You don't have to stay there. It's up to you. Hey, everybody. Thank you for joining us today. Can I visit with some of you? We're live, and our program will begin in about 10 minutes from now. Once I say hi to a few of you, I'll share my already tale of woe with technology. What else is new? Where are you viewing from? Can we say hi to a number of you? Yeah, that's the Rock Liquor. Hans from the Netherlands, Tri-Cities, Troy, Oregon, Gunnison, Colorado, Port Orchard, Burlington, Washington. Hello, Andre in Germany. Edmonds, Washington, Marysville, Washington, Forest Grove, Oregon. Let me go down to live. Payette, Idaho, Lake Oswego, Oregon, Fabian, Alberta, Marysville, Washington, Edmonds, Washington, Big Tussle, Oklahoma. Are you making that up? The Netherlands, Spokane. Hi, Connie. Haverhill, Massachusetts. We have Walter Zaliga from Massachusetts correcting me in real time, saying it's Haverhill. Oh, yeah, you home stickins. What the? Tried to do okay. Morton, Washington, Marysville, Washington. Is Tim Melbourne here, by the way? Who's manning the 504 ship? Yeah, okay. Charlotte, another Netherlands, Salt Lake City, Utah, Seattle, Fault. There's Erin Donaghy and Heina Shamlu, dressed in black. I missed the memo on that. We will check Erin's microphone. These are brand new microphones, courtesy of Nat Nichols' technological help. Since you've reported 5x5, then I'm going to assume that you can hear me just fine. So kind of cordless, wireless, whatever, like we tested it last night. Central Oregon coast. Terrific. So I'll just share with you very briefly, and then we'll turn you around and let you enjoy the room for a second. I had everything set up. I hit go live, and it said live streaming not available. And it had options to like try again. So I'm like, try again, nothing. And I could see you guys in the live chat. And then what did I do? I panicked, swore, and then I guess I just refreshed in my browser, and that did it. So that's mainly me talking to myself for future episodes to remember to do that. Thank you, John. Yeah, the profanity did the trick. Okay. So let's have you enjoy. The room's filling in quite nicely earlier than usual. We still have 8 minutes before the beginning of our program, so we've got a lot of extra people. We have Bobby from Hood River, Oregon, visiting today. We have Jerry and can't remember his wife's name from Bellingham. We have Steve from Liberty, gold mine area. We've got a couple others. I got Dad of Tyler, it looks like. Let me show you. Thanks for joining us. Hope you enjoyed today's lecture.
There is a bug tussle, Oklahoma. And there's also one in Texas and in Alabama.
For real. Okay, one more check for me. You can hear my microphone, 5x5, please. Can you do Nick 5x5? And if so, then I'm going to go over and turn on Erin's microphone and we'll check that one. Nick 5x5. Thank you, Rob. Thank you.
We going live?
I think we're ready. Do you mind if I just work with your corsage here?
We already got through all of the non-live hot mic.
Got that out of the way? Right.
We're clean. We're good.
Good.
It's out of our
Now you're
system.
pure, right?
Now
now.
we're pure.
Okay. So chit chat a little bit more. People are going to hear you now. I'll see if they can hear you well.
Okay.
And
Testing.
are you feeling comfortable remote wise, or you know how to advance? You feel like you're? I think we're synced up. It's just.
But is this
forward
just
and
the
back.
forward and back? Oh. No.
Okay.
I can always use the,
I guess we might have
Use
to.
the arrows.
yeah.
I think I'm just pressing a little harder. You want to try again?
Fine.
Or maybe it was just you.
No, now it works.
Okay. Okay.
That's
Okay, Erin's 5x5. Good.
Come over here.
Very clear audio.
well,
Oh, good.
yeah, if you have to use the
Wonderful.
mouse, I might be over here.
Yeah. That'd be
So
Then the Zoomers can see it.
Thank you.
yeah,
Looks like we're ready to roll, but
always try
still
to
got 4
use the
minutes. We'll
mouse
go out in the
now.
hallway.
It's confusing.
You're hearing Erin talk to Hannah, and you're also hearing me as well.
Yeah. I'm used to walking up to the
Bellingham
especially
heading
in-
back tonight.
I've never been in
We hit back tomorrow.
Oh,
big
tomorrow.
hall like this,
Oh,
but in
what's
the
on the
smaller
agenda for the rest
classroom
of the day?
settings, you can just like walk right up to the board.
Good.
Do you teach it?
Yeah.
I TA Cetrat right now.
Well,
and
we're not
so
exactly
I do a little
Bellingham,
lecture
but
at
we
the
do
beginning
have
to
a
introduce
little
the
First
material
Friday
of
art
the
walk
lab.
thing tonight at 5 o'clock. It's out of Pierce.
Yes.
Gallery 1
Yeah, I love it.
is downtown.
Yeah.
That's where a lot of folks
So-
kind of congregate. So get a
It's
chance
fun.
to see some of the townies. Yeah. We got a ways to go to meet you guys, though. You got a lot going on. Yeah, totally. Okay. Okay.
Sometimes. Oh my
Nice.
gracious. Like the big thing on Memorial Day weekend. Ski to see thing.
Oh, right. Right.
Frankly, there's a little town called Odessa.
Uh-huh. Sure.
There's one motel there. Sometimes we go there
Oh, wow.
just because we know it's different.
No, you can't really. And it's
There's
really
Odessa elements
yeah,
here, too,
it's-
more often than
and
not.
it's kind of weird too.
Oh,
It
yeah.
might be at a
Cool.
podium,
Very
and
nice.
it might be similar to this, where your slide's almost behind you.
Right.
And then, yeah.
Okay, thank you.
So sometimes it can be really awkward.
Right.
You
You're
haven't
at,
heard
like,
about
an angle like
504,
this,
304,
so
and
you're
who's
seeing your
teaching that
slide
today?
at
Have
an
you?
angle. And I rarely look at the computer and present. I like look at the slides and present. So it's always a weird adjustment to like kind of get used to, and then they Zoom or they record as well now, and so you're encouraged to use the mouse computers. Which
Minimal.
may or may not work, and then, but it can be hard at the angle you're at sometimes to get the laser.
I think there are, this is, how much tsunami,
So
how high was the tsunami that arrived in Japan during Tohoku? Do you have a memory of that?
I've actually never been to AGU, so yeah, that's what I've heard.
On our shore.
Yeah.
The-
And the specific heights were unique to it.
oh, the Cordillera, yeah,
Washington rather than-
yeah. I haven't come to sign
Oh, in
or
Washington.
figured out what I'm doing yet. But that'll be nice.
then we're also going to GSA and bringing some undergrads to GSA because it's in Spokane.
Yeah. That's awesome. That's what happened with us.
Stick to your guns.
We were able
Stick to your
to
guns.
just drive to Pittsburgh for
Thank
the
you.
annual meeting.
This,
So we were
people are
able
going to be
to
fighting over these chairs
6 hours. So we were
in
able to
January
take
because they'll see the
some
replay of
undergrads
this and they'll go,
with
I want to
us.
sit next to Bryce.
Big cohort of grad students.
The famous rice.
When I was an undergrad, I was
They're all saying, is that the rock liquor? Is that the real rock liquor?
Yeah. It's kind of your first dive into the scientific
this is what
community.
this, and it was neat
Yeah.
because everyone was exchanging ideas. I don't know. It was fun.
Yeah.
Sorry, that was just good natured ribbing.
Yeah.
Get us to Massachusetts.
Oh, good-natured ribbing as opposed to the usual ribbing I get. Hello, Mr. President. Good to see you.
Larry.
Well, hi, Larry. I'm Nick.
Zentner, Nick on the Rocks.
Nice to meet you.
Oh,
Nice to meet you.
Between these two geologists.
Don't ask him what he's got plugged into his chest here.
Sneak through.
Thanks for coming, you guys. Hope you enjoy it.
Do you have a Nick? Okay, do you have an intro prepared? I didn't get her intro. Do you have one prepared? No, well, good. I was like,
Thank you, Hannah.
yeah. Usually I write one for him and then I forgot.
Okay, one more time. Can I check 5 by 5? We're about to begin.
No, I'm kidding. You're gonna be.
We have 380 here
Hello
watching.
here.
Thank you for being here. Thank you, everybody. Okay, let's get started.
Oh, the end. Take a sip of water. Yeah, yeah.
So looking forward to this. Thank you. I'm going to do a quick intro with me on camera, and then I'll hustle and get your slide up. And
Sure.
We'll be off and running.
Sounds
You can see it
good.
right there. Thanks. Hello, everybody, and thank you for coming today. As always, it's nice to see a full room. We now have someone sitting in the very front row, Bryce, the rock licker. Thank you, Bryce, for being so bold. Oh, round of applause for Bryce. All right, good. We have many guests from out of town. A special thank you and welcome to you. We're happy to have you stick around after the lecture if you'd like to meet some other folks in the room and get a chance to speak more with our speaker, who I'm sure that you will enjoy. A couple of quick announcements involving this series. Ann Egger is in the back of the room. She has some forms. If you have not yet this quarter signed them to either give permission to be on camera or to sign and say you don't want to be on camera. So if you haven't done that yet, please check with Ann on the way out today, and that will be good for the entire year, not just this quarter. Also, Tim Melbourne is right there in the blue coat, and he's teaching 504 and 304. If you need to check in with Tim for that class, please do so after the lecture. And this is the last of the Friday at noon talks this quarter. That's kind of unusual. The quarter still has quite a few weeks to go, but next week's a holiday on Friday, Veterans Day. Another Friday is a holiday for Thanksgiving, and then before you know it, we're at the end of the quarter. So this is it for us for the fall quarter. But Hannah Shamlou and I have been putting the schedule together for the winter quarter, and we have 5 speakers. Logan from the first floor is talking about landslides in the Northwest. Kelly Wall from USGS in the Portland area will come up to do a Goat Rocks volcano talk. Susan Kaspari from the third floor, a little closer to heaven. She will talk about her sabbatical and her Fulbright in Norway. Marie from the third floor, giving a talk probably on her dissertation from Oregon State. And Anthony Schoen is a geothermal expert coming over from Spokane. Susan hooked us up with Anthony, and I think he's involved with the campus project. And I'm pointing to the CWU president here who's with us today. We're honored to have him with us. So a full slate of winter talks. We'll get you on the email list. We'll let you know the details about those talks coming up. Anybody got anything to say before we talk about our speaker today? Yeah, man. Okay. So this is the last of our fall speakers, and Erin Donaghy is with us. She flew in from Purdue University in Indiana, landed in Seattle last night, and drove over this morning. She will be here the full day, and we'll be heading back to Seattle tomorrow at some point. So there's more than the usual amount of time to visit with Erin, and I know that many of you will be very excited by this talk today. And so if you want to stick around and visit in this room after the talk with Erin, with a subset of you, wonderful. If you have an office or something in the building and would like to have Erin come to your office and hunch over some maps or some samples or the laboratory or something like that, that's also a possibility. If none of that applies to you or appeals to you, 4 o'clock, Cornerstone Pizza, downtown Ellensburg, everybody is invited. So Hannah's got a table reserved, and many of us will be down there having pizza and beer and chatting with Erin as well. Okay, great. I keep looking at this, but I don't think I need this. This is a very special guest. Erin has been out here in the Pacific Northwest for many years doing field work in the Chumstick Basin between Wenatchee and Leavenworth. She's been doing field work up in Alaska, as you'll hear. She's been doing some field work out in the Olympic Peninsula. And many of you have seen Erin on YouTube because I've been able to follow her work from the beginning of her PhD up through now. And so whether it's live or field videos, we've gotten a chance to document this very talented geologist. She got an undergraduate degree from Bucknell, master's degree from Northern Arizona, and she's just finishing up her PhD at Purdue University, studying under Mike Eddy and Ken Ridgway. Would you please help me welcome Erin Donaghy?
All right. We good?
Yep.
Okay, well, thank you so much for that introduction. I'm really excited to be here talking about my research. I'm going to talk about my dissertation research, so kind of give a broad overview of what I've been working on the past 4 years. And so that's going to focus on understanding oceanic plateau collision and breakup in the Pacific Northwest. So this is a photograph of one of my field areas. I'm really lucky to be able to work in Olympic National Park. And so this is up standing near Mount Angeles, looking south towards the Olympic Mountains. So I'm really lucky I get to work in these beautiful areas, looking at all these different sedimentary and volcanic rocks. So this is an outline of what I'll go through in today's talk. I'll give a broad introduction on the Silesia and Yakutat Oceanic Plateau model. I'll identify the key scientific questions that my research is looking to answer. Then we'll walk through some of the methods that I utilize in my research before walking through the basin evolution of the Silesia and Yakutat Oceanic Plateaus. And then we'll conclude with a discussion on the origin and translation history of the Yakutat terrain. And so the goal of this project overall is to understand basin formation following the collision of an oceanic plateau to the Pacific Northwest 50 million years ago. So on this map here, you'll notice that we have these shaded purple regions. These represent fragments of oceanic plateaus. So we have the Silesia terrain down in the Washington and Oregon area, and we have the Yakutat terrain up in southeastern Alaska. And you'll also notice on this map that these fragments of plateaus are separated by this regional network of right lateral strike slip faults. And so a hypothesis that was recently popularized by Ray Wells suggests that these two fragments of oceanic plateaus once originated as the same composite oceanic plateau offshore the Pacific Northwest. So they have this initial collision together as a composite plateau. And then the Yakutat terrain has to break off and then be translated northward to where we know it's currently colliding today. And so the goal of my dissertation research then is to understand this collisional history of oceanic plateaus in the Pacific Northwest and Alaska. And by doing so, we can understand this debated origin and translation history of the Yakutat terrain. I realize that some of you may be unfamiliar with what an oceanic plateau is. And so oceanic plateaus are just over-thickened pieces of oceanic crust. Generally, oceanic crust is around 7 kilometers thick. And so oceanic plateaus can be up to 30 kilometers thick of basalt. And this model here on the left part of the slide, this is one of the more accepted models for how they form. And this is, you have this mantle plume. So it originates from the mantle core boundary. It rises up through the mantle, and then it impinges at the base of the oceanic crust. And this allows for this large volume of basalt to be extruded onto the seafloor. And when we think about where one of these might exist today, we can use Iceland as an example. And Iceland is a really great example for the Yakutat in the Silesia story, because we can see that it sits on top of the Mid-Atlantic spreading ridge. And so it's this ridge-centered oceanic plateau. And when I talk about colliding an oceanic plateau to a continental margin, you can kind of think of taking Iceland and slamming it into the west coast of the Cordillera. So what happens when we do collide one of these oceanic plateaus to the continental margin? That's really kind of dictated by the rheology of the plateau. So in the case of the Silesia oceanic plateau, or this early composite Yakutat Silesia plateau, it was still being constructed when it was collided with the continental margin. And as a result, it was very hot and buoyant and rheologically weak. So when it first collided with the continental margin, then it didn't want to subduct. And because it was weak, the subducting slab broke off, and you get a magmatic flare-up that forms above where this slab breaks off. You get this period of short-lived fold and thrust belt development. And then once you migrate your subduction zone outboard and you accrete this terrain to the continental margin, you remove that heat source, and it allows for thermal subsidence. And it allows for this regional phoric basin to form out on top of the oceanic plateau. And so this sedimentary basin is the basin of interest for this study. So using these sedimentary record to understand the types of collision that we're having with these different fragments of oceanic plateaus. But I talked about the Yakutat terrain being translated along the Cordilleran margin. And so as a result of this, the oceanic plateau, the Yakutat terrain, was much older by the time it collided with southeastern Alaska a second time. And so it took about 20 to 30 million years for that terrain to be translated along the Cordilleran margin. And in that time, it had time to cool. And so it becomes rheologically stronger. And so it will interact with the continental margin during this collision in a completely different way. So we would expect totally different tectonic processes, sedimentologic processes with this type of collision. So in this scenario, we actually have subduction of the oceanic plateau, but instead we have subduction at a very low angle. And so that's called flat slab subduction. And we shut off our magmatic arc, and we have this really long-lived phase of fold and thrust belt development. But we still have these sedimentary basins that form out on top of these oceanic plateaus. And so again, really to kind of understand this oceanic plateau history of collision and translation in the Pacific Northwest, we're going to look at the sedimentary basins that formed on top of each one of these fragments of oceanic plateaus to test this idea if they once originated as the same oceanic plateau, then when they were both situated off the Pacific Northwest, I would expect depositional environments and where sediments were being derived from to be very similar. And then once the Yakutat terrain broke off, I would expect to see very different depositional environments or where sediments were being derived as it made this northward journey. And so in today's talk, we're going to look at the Cenozoic sedimentary basins on top of each one of these fragments of oceanic plateaus to understand this history of collision and translation during the Cenozoic in the Pacific Cordillera. Okay, so now we're going to move on to the methods. And so how are we going to use the basin deposits to understand this history? I integrate various methods that range from high precision chronostratigraphy to more sedimentologic field work and provenance work to understand where sediments were being derived from and what those depositional environments were. So there's very strong field and analytical components to my research. And we first want to establish this really high precision chronostratigraphy because we need to understand the age of our basin deposits. And when we put this depositional environment and sediment provenance data into context of that high precision chronostratigraphy, we can start to really understand how depositional environments are changing or how sediment routing systems are changing. Because when these things change in a dramatic way or a significant way, it's generally tied to some tectonic process. So we can use this as evidence that we might have some big collisional event or translational event. And so we really want to have a detailed record of how these change through time as a basin is evolving. So we'll first kind of look at the high precision chronostratigraphy. I work with Mike Eddy, and he has a ID TIMS lab. And so this stands for chemical abrasion, isotope dilution, thermal ionization, mass spectrometry. What we're doing is looking at uranium, lead, zircon geochronology. So zircons are just minerals that we can extract from volcanic rocks. And when they're from volcanic rocks, they record the crystallization age of that eruption or when that magma chamber formed. And so when you date a zircon that's from a volcanic rock, it is the age of that volcanic rock. Sedimentary basins are a little more difficult to constrain the age because sedimentary rocks are just essentially a mixing pot of all the detritus that was eroded from surrounding source terrains. So when you date minerals in a sedimentary basin deposit, you're not getting the age of the sedimentary rock, you're getting the age of all the source terrains that it was deriving sediments from. So ideally, if you have a basin and it forms next to a volcanic center or some sort of magmatic arc, you might have these volcanic rocks or tuffs that are interbedded into your basin deposits. And if you can go in and collect these different volcanic rocks or tuffs, then you can date them with this high precision technique. And what that does is it brackets the sedimentary strata that are of interest. So then we can get an age. We know that all those sediments were deposited between time 1 and time 2. And so this is the best way we can really understand the age of our basin deposits. This is a really time-intensive technique, and I'll walk you through a little bit of it. So we're looking to date zircons by using the uranium-lead isotopes. And so what we want to do is separate the zircon out of the rock. So we'll collect these whole rocks in the field, we'll bring them back, we'll crush and pulverize them, we'll separate out the heavy minerals and then get zircon. And the first step of this process is to anneal those zircons. And we do this by sticking it into a box furnace at 900 degrees C for 60 hours. And what this is doing is it's bringing that zircon back down to its closure temperature, which one thing we're really worried about in uranium lead zircon geochronology is things like lead loss or any damaged part of the zircon, which if you lose lead, then it usually biases your age towards a younger apparent age because now we're measuring different uranium and lead isotopes that weren't the original values when that zircon crystallized. So in order to try to mitigate that, we do things like annealing and chemical abrasion, which will get rid of, you can think of it as the bad parts of the zircon or the zircon that experienced lead loss, so that what we're left with should be a more accurate part of the zircon that has not had any damage. And when we date that, we'll get more accurate uranium and lead values that will give us an age that is closer to the true age of that zircon. And so this is a picture of inside of our hood here in the clean lab. And so this is the microcap assembly. And so each one of these little microcaps, what we'll do is put a single zircon into each one of these. And we usually have 2 blanks in there. So we can only date 16 zircons or put 16 zircons at a time through our chemistry. So we'll put these in acid and we'll do chemical abrasion for 12 hours. That'll eat away any inclusions or the zones of lead loss in the zircon. And then once we've kind of rinsed all that bad leachate out, we'll dissolve the zircon entirely. And then this is what we're going to be able to date using the mass spectrometer. So we're not done yet. This process, like I said, is pretty extensive. Once you've dissolved the zircon and you've dried it down, you need to separate out your uranium and your lead isotopes. And so we do this with column chemistry. And then once we have those they're essentially little dots at the bottom of a beaker, we can take that and we can load them onto filaments using silica gel. And then we load all these little filaments onto the turret and we put that turret into the mass spectrometer. And then we can start our analyses. Each analysis will take about 2 to 3 hours to measure both our uranium and lead isotopes separately. But even though this technique, when you kind of add up all the steps, it might take anywhere from 10 to 14 days, and you can only date 16 zircons in that time, it gives us really high precision ages. So the uncertainty that we have with these dates is on the scale of, plus or minus hundreds to tens of thousands of years. So these are really accurate and precise dates. So they're really great for when you're trying to establish a basin chronostratigraphy. So the other part of my research is understanding depositional environments. So I do this in a way of measuring stratigraphic sections and doing detailed lithofacies mapping. And so this is really important in testing this idea if Silesia and Yakutat once originated as the same plateau, because if they were once together, we would expect that they had similar depositional environments at the time they were together. And so when we're out in the field, we'll be mapping the units by their rock types, maybe so lithologies, if some lithologies are associated with certain sedimentologic structures, and we kind of split these up into packages or map units. And then once we look at the distribution of all these different lithofacies, we make a interpretation on what depositional environment we think that it formed in. And depositional environments could be deep marine or submarine fan systems or rivers or alluvial fans. And so we can understand that by looking at the sequence of rocks that we have in the basin. And then the final part is we want to understand in this story is where did the sediment come from? And so that's when I use the term provenance. That's all that means is I'm trying to understand where sediment is coming from. And we can use a couple different techniques to understand this. So there's compositional indicators. So that would be conglomerate class counts and sandstone petrography, and then uranium, lead, zircon geochronology. So when I introduced the zircons that are dating sedimentary basins, I said, if you just took a sandstone sample from that basin, so if you had a basin here, the zircons that you dated in that sandstone would tell you the age of the surrounding source terrains. And so when we're talking about the detrital zircon geochronology, if you had a sedimentary basin here, they might be associated with a distinct lithology or a distinct age. And so if we can get both of those data sets, conglomerate class counts are really great because you can see this is an image of where we did one of the conglomerate class counts. It tells you the actual lithology of the source terrain that you're deriving sediments from. So you could see if you're deriving sediments from a granite or from a schist. So it's really great because you have an actual piece of your source terrain. And then when we couple this compositional data with our age data, now we have a composition of it, and you can date some of these clasts if they're big enough, and you have an age of the source terrain. So when we're reconstructing basin histories, then we can start to look at the map of where our basin's adjacent to and say, oh, well, do I have any 52 MA granites nearby? And we can start to reconstruct these sediment routing pathways, stick that into your chronostratigraphy, and you can see how that changes through time, and you can see how it changes spatially in a basin area. And so the uranium-lead zircon geochronology, for my thesis, we implemented a new technique where we tried to bulk abrade the detrital zircons prior to then taking it to the laserchron. And so we don't measure detrital or analyze detrital zircons in the same way that we do the ID TIMS. We use a different method called LAICPMS, which is laser ablation inductively coupled plasma mass spectrometry. And this is different because we don't dissolve down our zircons. So we'll separate out our zircons. Generally, you would just take that zircon once you separated it out. You could send it to a lab, and they'll mount them onto little epoxy plugs. So you have your whole zircon, and they polish down to the surface of that zircon, and then they fire a laser at it. And that laser, the material that's ablated off the laser, contains your uranium, your lead, all your different isotopes, and that's measured, and you can get a date of the zircon in that way. And this technique is really great because you can measure hundreds of zircons. So I think the Arizona Lasercon Center now has it down to measuring about 350 zircons or so in about 4 hours. So the caveat there is that the uncertainty is not going to be as good. So it'll be plus or minus 2 to 3 million years for probably something that's Cenozoic age. We tried to bulk abrade our detrital zircons, so that's why you'll kind of see the CA, LA, ICP-MS. And we did that in order to try to improve the resolution of our age data. So if we did the chemical abrasion prior to laser ablation, would we see an improvement in the precision and accuracy of those detrital zircon dates? I want to make sure everyone knows how to read a probability density plot because we're going to be looking at them from here on out as we go through my data. So when you finish at the Lasercon or get your data set, it comes to you in an Excel spreadsheet. And we want a visual way we can look at these sandstone samples and understand the proportion of the ages that are contained in that sandstone sample. So what are the ages of the source terrains that are supplying sediment to my basin? And so on these diagrams, you have age on the x-axis and then probability on the y. And so when you plot it up, you get a bunch of squiggly lines, and then the peak heights are relative to the proportion of that age population in your sandstone. So the tallest peaks are going to be the ones that have the most ages associated in that sample. So you could quickly look at one of these PDPs and you could say, well, I have this big 160 MA peak and I have this 120 MA peak. And you start to get an understanding really quickly of where or the age of the source terrains that your basin was deriving sediments from. Okay, so now we're going to start walking through some of the data, and we'll start with the Silesia Plateau. And so we're going to jump out to the Northern Olympic Peninsula. So the next slide I'm going to show you will be a close-up of the Northern Olympic Peninsula there. And this is a simplified geologic map of the Northern Olympic Peninsula. So these purples here, this is the crescent formation. So those are going to be your basement oceanic plateau basalts. And then the basin deposits that we're interested in that sit right on top of these oceanic plateau basalts are known as the peripheral rock sequence. And so this is all of these brown units that are sitting on the northern part of the Olympic Peninsula. And overall, this sequence of rocks is characterized by deep marine submarine fan deposits. So it's overall very fine-grained, with one exception that this wire formation is this really coarse-grained conglomeratic unit. And then you'll also notice here that all of these basin deposits and the basement basalts are separated by this network of large faults on the Northern Olympic Peninsula. So over here is a simplified stratigraphic column. So if you haven't looked at these before, the oldest rocks are at the bottom and then the young towards the top. And so this is showing the sequence of our sedimentary sections sitting right on top of our basement basalts here. And this shows the stratigraphy that's associated with each one of these distinct fault blocks. And so we're going to walk through these different units from the lowest, the most basal unit sitting right on top of the plateau basalts, into the uppermost part, and we're going to put it in the context of Silesia's oceanic plateau collision. So we start with the lowermost Aldwell formation. You can see I've grayed everything else out on this map, and so the unit of interest here are these black units. Overall, this unit is very fine-grained. It's characterized by these massive lithic rich siltstones and mudstones. You'll notice that the map pattern is pretty discontinuous, so it's not making these really thick continuous packages. And we dated some of the rhyolites and tuffs that were interbedded in the lowermost part of that sequence, and they both yield ages that are around 52.1 MA. And so what this tells us is that these siltstones sitting out on top of our basement basalts actually predate the collision of Silesia at 50 MA. And so what we think these are these pelagic to hemipelagic basin deposits that were formed on top of the plateau, and they rode in on the plateau before it collided. If we look at the overlying unit, so now we've just jumped up to the Lyre formation, And again, this is that unit I mentioned that's really coarse-grained, that's really conglomeratic. You can see that it forms, again, these really discontinuous lenses along the northern Olympic Peninsula. And it is characterized by these cobble conglomerates to either sandy pebble conglomerates. It coarsens towards the west, so out on Cape Flattery, you even have boulder breccias. And then what's really important is that it's separated from those underlying pre-accretion siltstones by an angular unconformity. So you can see your Aldwell siltstones are coming up and they're folded, and then you have this big, massive sandy conglomerate of the Lyre sitting right on top of it. And so I'm going to put these lowermost units into context of Silezia's collision. So when we're looking at this, our DZ data is on the left. And then these are cross-sectional views of the maps that are on the right here. So it's a cross-section through our Silesia Plateau to the continental margin. And so when we look at this initial phase here, the Aldwell Formation, again, we think this represents this pre-accretion sequence, these hemipelagic to pelagic basin deposits. So their deposition was probably controlled by pre-existing topography on the Oceanic Plateau. And then when we look at the detrital zircon data, I really want to stress that overall, these rocks were very poor in detrital zircons. Just to get these 90-some zircons took a massive amount of effort. And this is just from one sample that was towards the eastern part of the Olympic Peninsula. And these age populations are very similar to what we see in the Western Melange Belt. And the Western Melange Belt was what was serving as our backstop during the collision of Silesia. And so it's likely that as Silesia approached the continental margin, we were starting to get some influx of sediments from the continent that reached out onto the plateau. When we move up to the Lyre Formation, we believe these are syn to post-collisional deposits. So we've now collided Silesia with the continental margin. We get this regional exhumation, this period of fold and thrust belt development. So the Aldwell and the Crescent, they're deformed in a series of folds and faults that are kind of isolated to those units. And then we have this influx of coarse-grained material. We think at this time you're migrating your subduction zone outboard. And then the detrital zircon spectra, again, we see these kind of age populations that are similar to the Western Melange Belt. And then some of these younger ones could also be tied to the Nanaimo group on the southern Vancouver Island or other source terrains that are kind of in that region. So very proximal derivation of sediments or even reworking of our underlying Aldwell and our underlying basement basalts. So if we continue to move up sections, so it's sitting right on top of the Lyre conglomerate, so we've collided the Silesia Plateau now. You can see that this Hoko River Formation here, they have a much more continuous deposition of this unit across the northern Olympic Peninsula. You have a much thicker stratigraphic thickness. And then overall, this unit is really characterized by lithic rich sandstones and mudstones. And in some places, we even have these really conglomeratic units. So this is a boulder conglomerate. And this is actually a piece that I'm pointing to of columnar basalt that's in this boulder conglomerate. And so most of the detritus in this unit looks like it's derived, it's basaltic. And so when we take a look, well, I guess we're going to take a look at the Macaw. But if we move up section to the Macaw Formation, we continue to see this increase in the stratigraphic thickness, so this regionally continuous units across the northern Olympic Peninsula. And we start to see this increase of more feldspathic to quartz-rich material. So we start to get more sandy units that are interbedded with the turbidites. And then when we kind of put this into context of our collisional models here, when we take a look at the Hoko River Formation, again, this is the one that was really enriched in the basalt detritus. When we look at the DZ data over here, we have these unimodal peak age population that matches the age of the Silesia basalts. Again, these were very poor in detrital zircons. And now we probably know why, because the majority of the sediments were being derived from basalt, and basalt doesn't have a lot of detrital zircons. So we think at this time that you have enough subsidence that we're getting more regionally continuous basin deposits, but the majority of the sediment is just reworking the underlying basement basalts that are either exhumed during that fold and thrust belt development or pre-existing topographic highs. By the time of deposition of the Macaw Formation, when we have this influx of more feldspathic and quartz-rich material, this is right at the Eocene-Oligocene boundary. We think this is when you start to get this formation of this regional forearc basin. So if you might have heard about the Tofino-Juan de Fuca forearc basin, these basin deposits look similar to basin deposits that are Oligocene on the southern tip of Vancouver Island, known as the Carmana group. And so this is really good evidence that when we look at the DZ data, we look at the compositional data, that we've had enough subsidence now that we're getting sediments derived from the continent at this time, and we've established this really broad forearc region. And so in summary, when we think about this as being a really good example of we're colliding an oceanic plateau when it's really hot, we see strong evidence in the sedimentary record that we have this slab breakoff and outboard migration of our trench. And we have the short-lived fold and thrust belt developed that deformed our pre-accretion sequence, so our Aldwell and our crescent. And then we get this thermal subsidence once we remove that heat source and we've docked Silesia, we've accreted it, that allows for establishment of a regional forearc basin. Okay, so now let's go look at the basin record on the Yakutat terrain. And so on the next slide, I'm going to show you, we're going to be all the way up in southeastern Alaska now, up in the armpit here, looking at the basin deposits on the Yakutat terrain. And so this is a simplified map of the areas where we worked. This is a little location map to help you locate where we are in Alaska. It's a very big state. And so on this simplified map, all these grays and browns, they represent those Cenozoic basin deposits. And you'll see these three different areas. This is the three different areas that we looked at these basin deposits. This is a huge area. If you notice the scale down here, just between area A and B, they're over 100 kilometers apart. And so we had to look at these basin deposits across this broad area to try to understand how our depositional environments may have varied. Was provenance varying in the same age sediments across this region? Was it changing stratigraphically through time? And so you'll see our simplified stratigraphic columns here for the three different units. If we want to look at the oldest part of the stratigraphy, we have to go to this easternmost area A in the Samovar Hills. And this is the only place we have that basement sequence that is exposed onshore. And so we went out to the Samovar Hills. It's a very difficult place to get to, but we made it. And we were able to sample these lowermost sedimentary basin deposits as well as the basement basalts. On the Yakutat terrain, these are known as the Hubbs Creek volcanics, and they are really just characterized by a series of basalt flows, agglomerate and tuff. It's about 200 to 300 meters thick where we sampled it. And what's really exciting is we were able to date one of these interbedded tuffs. And this is the first age that we have from these onshore basement basalts on the Yakutat terrain. And what's really exciting about it is that it matches the oldest part of the Silesia terrain, which is exposed in Oregon. And so we have our high precision age of around 56.295 MA. And so this is really strong evidence that the Yakutat and the Silesia terrain once originated as the same oceanic plateau offshore the Pacific Northwest. So let's take a look at the lowermost basin deposits here. So the lowermost unit, again, is it's another sequence of massive siltstones. And so these are known as the oily lake siltstones. We were able to date a tuff that was interbedded in this sequence, and it's around 55.7 MA. So we interpret that this thick sequence of siltstones to represent, just like in Silesia, these pre-accretion pelagic deposits that were sitting on top of that fragment of oceanic plateau prior to its collision. If we move up to the next unit, we separated this out as the Marvitz Creek unit. And what we have is from this transition of deep marine and the oily lake, we go to more shallow near shore deltaic and tidal deposits. And then the whole sequence is capped by a red paleosol. And then overlying that is the Coltieth Formation, the Eocene Coltieth Formation. And so this is going to be the unit that records Yakutat's translational history along the Cordilleran margin. But what's really interesting about this sequence is that we see this influx of coarse-grained material right at the base, and it is separated by those underlying pre-accretion units by an angular unconformity. And so I don't have nice basin cross-section figures for the Yakutat terrain yet, but hopefully in the next 4 months as I finish my thesis, we'll have those soon. But I do kind of have this tectonostratigraphic diagram. And so we looked at these pre-accretion units, and then this red paleosol was at the top of that pre-accretion unit. And so we see this sequence of exhumation, and then we have this angular unconformity. And we believe this marks that first initial collision with the Silesia terrain to the Pacific Northwest. And then what we're going to look at next to understand the translational history is going to be the Coltieth and the Pole Creek Formation. So these Eocene to Oligocene and even Miocene units. And the Pole Creek separated from the overlying Yakutaga by another angular unconformity. And so that represents that second collision with the margin of Alaska. And I'll just note that the Coltieth and Pole Creek, these units, all of these units are highly deformed and a very big fold and thrust belt. And so when we're starting to think about this hot and cold collision, when we look at the Yakutat terrain, the second collision now, once it's had time to cool, it's behaved entirely different than what we saw with the Silesia terrain. We have the subduction of the Yakutat terrain, this flat slab subduction. So this red line here kind of marks its margins of the Yakutat terrain in the subsurface. So you can see it extends all the way beneath south central Alaska, all the way to Denali. And this flat slab subduction drives some of the highest topography that we have in North America. You have Mount St. Elias sitting right here on the Gulf of Alaska. And so you go from sea level to 18,000 feet in almost no distance at all. So this is a significant orogenic event that we see with the second collision of the Yakutat terrain. So we're creating huge mountains with this style of collision. Okay, so let's conclude with talking about the translation history of the Yakutat terrain. And so again, we want to test this idea. Did Yakutat and Silesia have this early shared history? Well, we're going to understand how far the Yakutat terrain has been translated. We have to know where it originated. And so if we take a look at these basin deposits, just the lowermost sequence on both terrains, I've added in Oregon here as well, because that is the southern part of Silesia. We start to compare the sequence of the basin deposits. And so we can see on both Silesia and Yakutat terrains, we have this pre-accretion sequence of massive siltstones. In Oregon, this might be these siltstones of Trask River. They have not really been that well studied, so that could be an easy target of where to look for it in the Oregon part of Silesia. And we see this angular unconformity that separates this influx of really coarse-grained material. And so we see the same sequence of events. Even in the Oregon side, you have big angular unconformities separating your pre-accretion from your post-accretion packages. And the only difference here really that we have to think about is the timing. So you can see that on the Silesia terrain, we have a little better chronostratigraphy, so we can date this angular unconformity a little better, versus on the Yakutat terrain, we have the basement basalts at around 56 MA, we have those pre-accretion deposits around 55.7, but then the next date we have is somewhere in the middle of the Coltieth around 43 MA. So we don't really have as tight of an age constraint for this angular unconformity that would mark that first collision with the Silesia Plateau. And so this is really important when we're going to think about, and what I'll be working on, and these next 4 to 5 months, is what were the geometries of these plateaus together and when did they start interacting with the different parts of the Cordilleran margin? Because the Yakutat with these dates could have interacted much earlier than Silesia, all depending on the geometry of that plateau as it approached the continental margin. So those are just things to kind of keep in your mind and things that we're actively thinking about as we proceed to kind of make reconstructions of the Yakutat translation history. And so what we want to do then is look at that detrital zircon record of the Coltieth to compare it to the known ages that we see in this big pink blob here on the map, which is known as the Coast Mountain batholith. And so the original idea of why we did that bulk abrasion of those detrital zircons was to try to improve the resolution of our detrital zircons in order to see if we could be able to discern between these different magmatic flare-ups that we see along the Coast Mountain batholith. So this is the age data for the southern to central parts of the Coast Mountain batholith. And so we want to be able to tell when, based off of the provenance and the Yakutat deposits, when we were deriving sediments from these different source terrains and at what time. And so what we're going to do now is we're going to walk through the detrital zircon data from the Coltieth. These reconstructions that you're going to see on the next slides are very preliminary. They're just kind of to get discussion going, but give you a general idea of where we think at least these fragments of the basin deposits that are left, the ones that we've looked at, which are again caught in this massive fold and thrust belt, where were they deriving sediments from and at what time? So you can see that we've sampled the Coltieth Formation in the Pole Creek. We try to hit the middle, the lower, middle, and upper parts of this sequence, and we try to hit that in each one of these areas so that we can understand how provenance changes through time as well as spatially. And so we'll start with, I'll just remind you again, what I've done is I pulled these little the age spectra from the Coast Mountain batholith, and you'll see them kind of sitting up in the corner here, and we'll have our reconstruction. So if we look at the detrital zircon data from those lowermost basin deposits, so this is the pre-accretion sequence, when you take a look at the oily lake siltstone, you can see it has peak age population that just matches the age of the underlying Yakutat basalts or Oceanic Plateau basalts. Again, the Aldwell has a little bit of variability, but that could just mean it was situated closer to the continental margin at that time. As we start to move up section on the Yakutat terrain in these lowermost deposits, you'll see this Yakutat group here is part of the Yakutat terrain basement. And this is probably when the Yakutat terrain collided that first time. You'll see this Chugach terrain, a piece of that kind of got stuck onto the Yakutat terrain. And so that's part of the Yakutat basement. And when we look at the basin deposits that sit right on top of the oily lake siltstone, we see detrital zircon spectra that look very similar to this Chugach terrain or this Yakutat group. The gray spectra here represent the basin deposits, and then I've just overlain the different parts of the Coast Mountain batholith spectra onto the DZ spectra. Okay, so we'll move up through the Coltieth. So this is the Coltieth Formation. This is the basal conglomerate. Again, what we're seeing is that when we look at this Bella Coola area and the terrace area of the Coast Mountain batholith, that the detrital zircon spectra, it looks very similar to that underlying Yakutat group. So we're probably deriving sediments either from when we exhumed that in that initial collision or this adjacent Chugach terrain. But we're also seeing some of the spectra look close to this terrace Bella Coola area, but it's not distinct. You couldn't tell exactly, oh, it must be coming from this area. It almost looks like a mixed kind of signature between both. But what we do understand, though, based off of this, these basin deposits that we're looking at, we're probably interacting with the margin at the central part of the Coast Mountain batholith. And so if we continue to move up section and we start to look at some of these younger basin deposits, you can start to see that the peak age populations start to change, and it looks nearly identical to the terrace age spectra. And so by this time, we can be pretty confident that the Yakutat terrain is deriving a lot of sediments from this terrace area of the Coast Mountain batholith. So we see this distinct change in provenance as we're moving up section towards these middle to upper parts of the Eocene Coltioth formation. And then I want to point out that these could possibly be the same age. So this is, again, talking about how sediment provenance could be changing spatially in a basin, that this has this more mixed result, and this has this more distinct this looks like the terrace, that these could be the same age strata. We don't have high enough precision age data to really fully understand the chronostratigraphy here. And because this one's situated more north to this area as it was being translated, they could have just been deriving sediments at the same time from different areas. So we have to kind of consider that in these models as well. But if we continue to move up section, the rest of the strata we see here, it has this really strong signature that matches closely to the terrace area. So at least by the time of deposition of the Eocene to Oligocene Pole Creek formation, we have strong evidence that sediments were being derived from the terrace area. And so kind of using just the detrital zircon data right now, this initial collision, at least of the basin fragments that we see that are preserved on the Yakutat, show that they were deriving sediments from a more central part of the Coast Mountain batholith. So that really gives you a minimum constraint of about 1,000 kilometers of translation of the Yakutat terrain since deposition of these sediments. But we also want to recognize that these plateaus are really big. There could be parts that we're not seeing that were closer to where Silesia was. So these are all things we have to think about when we're doing these reconstructions. And this is, again, is just kind of showing the Pole Creek formation now. So this Oligocene to Miocene unit, you see this really strong indication of that terrace area. So we're still deriving sediments from the terrace area at this time. This is a really cool unit that definitely needs more work, has all these interbedded mafic volcanics into it, which could be pretty interesting to understand the geochemistry of those, or why we're getting all this mafic volcanism. Does it have to do with, leaky transforms as this thing's being translated northward? Does it have something to do with the collisional process of the Yakutat terrain? More age data, chronostratigraphy would be really great to understand the age of these deposits and then put that into context of its translational history. And then again, we have deposition of the Yakutaga formation. By this time, Miocene, we have this huge angular unconformity. So this is a really great photo. Oily Creek would be right in front of me in this photograph. To the right of that photo, you have your whole kind of Marvitz Creek unit, the Coltioth, that records our translation history, and then this big angular unconformity. And that really marks that second collision with southeastern Alaska. And so I'll conclude with just some summary thoughts here, but I hope that you've learned from this talk that you can really use these basin records as indicators for understanding tectonically what's happening. So basins are excellent recorders of tectonic processes, and understanding the depositional environments and where sediment routing systems are, how they're changing, where you're deriving sediments from, can be really great indicators of these larger tectonic processes that are going on. We believe that our data shows that Silesia and Yakutat have this early shared history, and if we can start to use this basin record to really understand the translational history of the Yakutat terrain and test some of these models that exist out there for various transport distances of the Yakutat. I will conclude there, so there's some time for some questions. I'll leave the acknowledgement slides up, but I mean, my advisors, Mike and Ken, have been fundamental in mentoring me through my PhD. So, I really want to thank them for all their guidance. There is a lot of different people that have put in funding and organizations into this project. I've had a lot of field assistance from undergraduates who've gotten to work with me out on the Olympic Peninsula. Working with the national parks in both Alaska and Washington have been great, as well as the logging companies out here in Washington have always been great, giving me access to their logging roads to look at these rocks. And our Alaska work, our pilot, Steve Richards at Ridgeline Aviation, was fundamental for making that field season happen. So yeah, I'll leave it there for some questions, but thank you so much for your attention.
Questions for Erin? And Erin will remember to repeat the question for our home viewers.
I will now.
What paleomag data exists for the Yakutat terrain, and how does that match with the rest of the story?
We don't have paleomag data, so it would be really great to get paleomag data. And that was something that we had talked about, trying to get someone to go into the field with us, and then it didn't end up happening. There might be some paleomag data, but nothing from onshore. So it would be great to get it for the Alaska stuff.
I'm sure there's more questions.
Yep.
Yeah, because Silesia was so hot when it hit a large mass like that, it's going to shrink when it cools. What sort of effect would that have on the inland fissures? I always think of the Liberty area. Could that help split in Silesia and Yakutat?
The inland what?
The large hot mass, as it cools, it shrink, have a little bit of pullback effect on the contact. I'm just wondering how that affect some of the inland fissures, and could it help with that split of Silesia and Yakutat?
Okay, so the question was, when you collide a really hot oceanic plateau and it has to cool, would that, how it impacts the structures inboard of the collision zone? So we have a really great record of kind of the inboard processes that are associated with Silesia's collision. And so really at this time, we collide this really hot oceanic plateau, and you have that slab break off. And so you have a lot of extension at that time. And we also see that this is marked during this period of really accelerated strike slip faulting that happens right after we collide the Silesia plateau. So this is when things like the Strait Creek Fault are going, the Leavenworth, the NTAT. We have all of these strike slip systems start to activate, or well, they were already active, but they accelerate at this time. And we see kind of fold and thrust belt development in the SWOC. So the SWOC basin is deformed. That was kind of your Paleocene to Eocene forearc basin. That gets deformed, and then it gets intruded by the Teanaway volcanics, which probably formed during that slab breakoff. So all those dikes, this large outwelling of volcanism, and then this accelerated period of strike slip faulting. So that's kind of really our inboard history of the collision to the Yakutat terrain. But it does take time, based off of the work that we've done on the Olympic Peninsula, for you to actually be able to establish some sort of regional forearc basin. We don't really see evidence of that until the Oligocene. So there's some time between collision and then establishment of a regional forearc system. Yeah.
Erin, great talk. I am really fascinated by that almost unimodal DNA peak that you have. It looks like you have older sediments that have that western Millennium Belt signal with a lot of rotating circons. And then you get this unimodal peak, and we're arguing for just a local derivation of that. Could you elaborate a little bit on what sort of scenario might be involved where you're getting derivation presumably from Silesia, but not in recycling those earlier deposited sediments?
Yeah. So the question was about the unimodal peak age populations in the Hogo River Formation. So this unimodal DZ population that matches the age of the underlying Silesia basalts. And that was really shocking for us when that data came back. And, we those three kind of DZ spectra in there were from the lower, middle, and upper part. So it's consistent throughout the entire thickness of this unit. And if you move towards the east, so that sample, let's see if I can get back there. Sure. So those three samples were collected here. So you're kind of out on the western part of the Olympic Peninsula. And then recently I went back and I collected one, let's say right over here in the Hogo River Formation. And so this has a different detrital zircon spectra. you still get that peak age population of 50 MA, but you also have that strong signature of the Western Melange Belt ages. So something happened here, whether it was the kind of dictated by that pre-existing topography on the plateau, or whether we created some sort of structures during that collisional phase and had some create new topographic highs that isolated that part of the basin from the continental margin, because we only see reworking of the Silesia terrain there, those Silesia basalts. But we do have some evidence that sediments were starting to make it out from the continent when you move out towards the east. So maybe it's this time transgressive thing that just took sediments longer to reach all the way out to this western area. These are large areas, or at that time, this basin, after the collision, it was in its own little isolated basin because of some sort of structural control. Yep.
Papagino at home asks, were Yakutat and Silesia subaqueous during accretion and deposition?
So Silesia, the parts of you have the lower and the upper part of the crescent formations, and so they record this transition from submarine to subaqueous to subaerial, even some parts of the upper parts of the crescent. And then for the Yakutat terrain, we see strong evidence that it was subaerial because we got Paleosol development. So you can't have Paleosol development underwater. So we know that by the stage of right before Silesia, or the Yakutat-Silesia composite plateau collided, you had enough exhumation that we see this whole sequence from deep marine to shallow marine to tidal, and then we have Paleosol development. So we know that that part where we're looking at the Yakutat terrain was subaerial by the time it collided.
Two more?
Okay, so the Blue Mountain unit, I actually put slides in backup just because I knew. So the Blue Mountain unit is this pink unit on this map here, and it's in this really interesting structural position because it's behind the crescent basalts, our basement basalts. And so original interpretations were that this was interbedded with the lowermost part of the basement basalts. But work that was done by Mike Eddy, he dated some of the sandstones. So he did detrital zircon geochronology. And when you look at the youngest cluster of zircon ages, you can get what's called a maximum depositional age. So you know that those sandstones had to have been deposited at that age or younger. And so the MDAs for those sandstones were around 45 MA. And so the Silesia basalts are 56 to 48. So that means if they were interbedded, this has to represent some phase of volcanism that's way younger that we haven't really thought about, or well, that's really the only interpretation. So, or they're faulted. Essentially, if they're not interbedded, they have to be structurally underthrust beneath they have to be thrust beneath the crescent basalts. And so, how I've been looking at the Blue Mountain unit with this, we went out, and this was an extensive part of my 2021 fieldwork where we did lithotheses mapping and tried to understand this relationship. Is the Blue Mountain unit interbedded, or is it structurally juxtaposed against the crescent basalts? And what we found and how we're interpreting the Blue Mountain unit is that you kind of have this distinct set of volcanic facies that's associated with the Blue Mountain unit. So you get these basaltic tuffs and basaltic breccias interbedded with these really deformed argillites and sand. You get these weird red carbonates, pillow basalts. This looks like classic ocean plate stratigraphy to me. And then you have other places that you have these really nice turbidites, so these sedimentary facies. And so how I'm thinking about this would be that those are trench turbidites, and this is ocean plate stratigraphy. And what the Blue Mountain unit actually represents is part of the subduction complex. And so it would be an ocean plate stratigraphy type melange that marks kind of the earliest formation of our subduction complex. And so we think the basin record on the Olympic Peninsula shows us that we're starting to get this regional phoric basin, sediments derived from the continent out by, 45, 40 MA, that if sediments are also making it out to the trench, then we could be forming our accretionary complex at that time.
I think that's a good place to end it. Hey, let's thank Erin. Come on up and visit with Erin if you like. Thanks for coming. If you want to join us at 4 p.m., Cornerstone Pizza and egg are on the way out the door. Thanks, guys. See you after the new year. Goodbye. Nailed it once again.
Thank
Perfect
you.
timing, the whole thing. How'd it feel?
It's good. It's good. I enjoyed it. It was a lot of fun.
You're a pro by now. Yeah.
I had fun with it.
Tons more people with questions in the live chat. 600 people watching live, way more than we normally have. So,
Awesome.
okay, well, let me take the mic from you.
Oh, yeah.
I'm going to talk to those folks a little bit more. We'll see who comes up. We'll just play it by ear. And I'll just read how you're feeling, basically, and if we want to just keep going in the department or if we just want to get back home and just unplug for a little bit. Okay, thanks. Okay, let's say a couple final words before we sign off here today. Sure do appreciate you joining us today. What camera are you? What the hell? Hang on. All right. Thank you, Balake. Okay. I'm confident in saying this. That was a great talk, and if you were disappointed in that talk, you've got a problem. I don't know what you were looking for, but how could you not be pleased with that talk? It had everything. Come on, man. Photography, maps, brand new information, tiny levels of detail, all the way to regional stuff from Alaska down to Northern California. Come on. Holy cow. Yeah. Terrific. That's university president behind me there in the black vest. I don't know if he wants to be on camera or not. He probably doesn't, so let me get him off. A couple final words. If you're just joining us, I'm pleased with this Friday at noon series. I am hearing from some students, potential students at other universities or community colleges or even high schools who watch some of these, and they can actually see who's in the room. They can actually see what they are going to join if they come here and study geology, which is one of the main reasons that I'm doing this in this particular way, to show the room, to show interactions between people. And it's working. So I personally am pleased, and to have so many of you watching with us live, that's just a bonus. But I think I've said this in different forms. This is a live stream, but you are not the focal point like you are with other live streams where there's a lot of back and forth. And I'm comfortable saying that it's so great that so many of you show up to join us live. But clearly, the interplay between the speaker and the people who are physically in the room is kind of first order, or the highest level of importance, basically. So just to remind you of the goals of this particular series, these Friday talks, it's having you kind of be a fly on the wall, and it's ultimately a way to feature speakers, especially young people, who are very impressive and have their whole careers ahead of them, and also to showcase this place where we have a good thing going and have for a long time. But to have the oldest guy in the department, working actively with the youngest person in the department, Hannah Shamloo, is a nice little bookend thing to put these speaker schedules together. Speaking of which, we will resume this talk series in wintertime. And these are the 5 Friday at noon talks that we're having in wintertime. And I don't have formal talk titles from these folks yet, but winter's a tough time to travel. And so Logan, Susan, and Marie work in the building. So we're going to be featuring them again in the name of featuring our department and essentially recruiting people to come work with these people. But Hannah's working closely with Kelly from the USGS. They have a project in the works on Goat Rock's volcano. And Anthony is, I think, tied to the university with a new geothermal project. So he'll be talking about geothermal energy. I think he's based out of Spokane, although I'm not sure about that. Before I say goodbye to you, we still have more than 450. It's official. I'm done thinking about this setup for the fall Friday speakers. And we're beginning Ice Age Floods A to Z this Thursday. You heard it here first. This weekend, I'm going to make a quick announcement video where I'm going to share the schedule, but I'm doing it with you right now for sure. For sure. This winter, A to Z, Ice Age Floods, live streams, Thursdays at noon Pacific, Sunday mornings, 9 a.m. That's different from the past couple of winters. Thursdays at noon, Sunday mornings at 9 from my office. And there's all sorts of reasons for that new room and new schedule. And I'll fill you all in with this announcement video that I have, culminating in 3 brand new downtown lectures, April 3rd, 4th, and 5th of 2024. So more coming on that. But we are turning a page on this channel from Friday noon talks and field videos to all systems go with the Ice Age Floods A to Z live stream series. Hope you can join us for some, maybe all, of the letters of the alphabet. 26 new live streams coming this winter. And with that, I say, here's to your health. Here's to the health of your parents and your grandparents. Here's to the health of your children and your grandchildren and your nieces and your nephews. Here's to your health, everyone in your community. I sincerely hope all is going well with you. And I hope that you find being here live as some sort of positive, safe place that you can be with like-minded people. I don't even think it's geology. I think it's just being in a healthy place. Thank you. I love you and goodbye. See you Thursday from my office.
This is a good exercise in
The dikes weren't protruded right when that slab broke off. So all those dikes cut through the swamp basement, and then you